I think it's recording. Hey class, how's it going? Welcome back to another day of learning science with Kegler, or physics with Kegler. Physics spelled F-I-Z-Z-I-C-S. Let's not waste time. So we've done a little bit of practice now on just Kepler's laws. We've done a little bit of practice going back on stuff that we learned revolving circular motion. We're gonna be now doing a little bit of stuff involving energy, just a little bit different than what we're used to before. We're kind of gathering all our physics knowledge together now to continue on from this point. So, excuse me, I have the hiccups, just ate lunch. Based on Newton's laws of universal gravitation, we know that increasing the distance between any two objects will decrease the force of gravity between the objects, right? The further two objects get from each other, the weaker the gravity is. The closer the two objects get towards each other, the stronger the gravity is. But in order to move the objects farther apart, work must be done on at least one of the objects, correct? If there are two planets floating around each other in space, or two planets, let's just imagine like two planets that are like here. If I want to move them apart, I have to do some kind of work, right? That requires some kind of energy. That means that there is some kind of potential energy in here. There is the school bell. This work causes the potential energy work that can be done by the force of gravity to increase in a way that is similar to stretching out a large spring. In general, we can say that at any separation distance r, the gravitational potential energy, PEG, between two masses, M1 and M2, is given by this important formula. The potential energy is negative G M1 M2 over R, not R squared, just R. Ooh. This gravitational potential energy has a negative value and approaches zero as R approaches infinity, right? If two items, what that's saying is if you have two items that are infinitely apart, like they are nowhere near each other, the amount of potential that these have are zero. And that means, in other words, the largest value of the gravitational potential is actually zero because it's negative, right? How can zero be the largest? Because if they are not infinitely apart, if they're closer together, it's going to have a negative potential that's going to be getting deeper and deeper into the negatives. And it occurs when, the largest value of the gravitational potential is zero and occurs when the objects are infinitely far apart. And since the potential energy decreases, becomes a bigger negative value. As the two masses come close together, potential energy decreases as the two values come together. We can call this situation a potential well, or in this case, a gravity well. We have a little diagram right here. It's pretty much showing the gravity well, or the potential well, of many different objects. One thing I really like about this diagram personally is it shows that there's no flat surfaces. Like at this point, you would be, or that's not a good example. Yeah, let's use that example. At that point, you are equally being pulled towards Earth and Venus at the exact same time. At this point, you're being pulled towards, I don't know what those two planets are. Oh, one's Titan, and the other one is Europa. Europa. Well, that sounds familiar. Regardless, you're being pulled towards both of those at the exact same time. Oh, this is a good example here, right? Boom. At that point, you're being pulled towards Uranus and Neptune at the exact same time, where you're kind of in equilibrium. But you're kind of always being pulled by these gravity wells by gravity constantly. And the reason why they call it a gravity well is because you can escape the gravity well. If we're looking at Uranus and we want to escape its gravity well, we would have to pass this point right here. to escape Uranus's gravity well. Same, you can go the other way, you can escape it over here and escape Uranus's gravity well going to the left. You can pretty much imagine this being the solar system where like all the planets are right here. The diagram might be a little bit hard to understand, but just note that this is our solar system going from left to right. Important formulas. We're going to talk about escape velocity. I've I don't know how the best way to explain this, but essentially, you can get so far away from a planet's gravity well where you don't feel its gravity anymore, right? Technically, you will always feel its gravity, like it's always roughly pulling you in, but you can still escape its gravity well, like where you're moving fast enough away where it's not pulling you in towards it. The minimum velocity required to escape from a planet's potential well or gravity well is called the escape velocity. For a rocket at rest on the planet's surface, the kinetic energy required to escape the planet is equal to the potential energy due to the gravity, right? That makes sense. The kinetic energy required to escape is equal to the potential energy due to the gravity. That means that our kinetic energy, which we know is this, has to equal our our kinetic energy has to equal our potential energy. We take the absolute value. I hope we know what absolute value means. I think it might be a little bit tricky for our applied / essentials friends, but it just means we take the positive value of our potential energy and we let them equal each other. And if we rearrange that formula a little bit, we get this handy dandy formula. This formula is used for escape velocity. Really useful. You take, it's the square root of 2 times g times the mass of a planet and divided by the radius of where you're trying to escape from. So, do you expect the escape velocity to be larger for Earth or Jupiter? Determine the escape velocities for both Earth and Jupiter. Let's do exactly that. For Earth, that is EARFF for Earth. Jupiter. The only things we really need to find out which one's going to have a greater escape velocity is we're going to need the mass of both planets, so the mass of Earth and the mass of Jupiter. And we're also going to need the radius of the planet, so the radius of Earth and the radius of Jupiter. So I didn't really talk about this, but on one of your other sheets, one of your assignments, quote unquote assignments, you should have a little chart that has the mass and the radius of all the planets in our solar system, and even some of the moons like Titan and our moon. But if you don't have that sheet or you just don't want to, you're too lazy to look it up like Mr. Kegler, what you could do is you could just Google it all right here, right? You could Google it right here. We can go mass of the Earth, 5.972 times 10 to the 24. That's pretty universally agreed. Where am I? No. Oh, what was the number again? 5.972. 5.972 times 10 to the, what was it, 24? Yeah, 24. And radius of the Earth is 6.8 times 10 to the something. Radius of the Earth, of the Earth, 6371. They spelled Earth wrong here. 6.371 times 10 to the 6. That was in kilometers. It said 6,371 kilometers, which is, this is going to be meters. By the way, yes, we want to do things in MKS units constantly, as always. Radius of Jupiter, 60, let's just round that to 70 70,000 kilometers. I think that would make us all happy. 70,000 kilometers. Um, or, yeah, let's make it 70,000 kilometers. That's 7.00 times 10 to the 7 meters. And the mass of Jupiter, is 1.898 times 10 to the 27. 1.898 times 10 to the 27 kilograms. We're all happy with that? Yes? No, you can't change any of the numbers. They have to be exactly these numbers. So if we want to find out which one has the larger escape velocity, let's throw it into this formula. We know that VR of the Earth is going to be the square root of g. Think about what the value of g is again before I spoil it for you. I'm not, once again, you don't need to have it memorized, but if you've done enough practice questions, you should roughly have it memorized. Don't forget that g is 6.67 times 10 to the negative 11. So I am getting 2 times 6.67 times 10 to the negative 11. I'm going to multiply that by 5.972 times 10 to the 24. And I'm going to divide that by 6.371 times 10 to the 6. I take the square root of that, and I am getting the escape velocity. The velocity you need to go to escape Earth is 11182 meters per second. That seems insane. That seems too high. Did I do something wrong here? Maybe I am right. Yeah, maybe it is supposed to be that high. Let's Google it. Escape velocity of Earth. Escape velocity of Earth. Oh, Earth. We spelled it wrong. Earth. There we go. Okay, we'll spell it normally. Escape velocity of Earth. Oh, no, that's right. 11.182 is what I'm getting, so 11.186. Oh, that makes sense. Okay, let's see the escape velocity of Jupiter. Once again, there's a few factors here. It is a much heavier planet, but the radius is also bigger. So it's what's more important here. What's going to be the bigger determining factor to see what the smaller, what's going to cause a bigger or larger escape velocity? What you should do is now throw this in your calculator, you know, the VR is equal to 2g m of j over r of j. So one of this point is going to be asking, why do we call escape velocity vr? I don't know. We use r just for the sake of, it's a nice letter. 6.67 times 10 to the negative 11 times 1.898 times 10 to the 27 divided by 7 times 10 to the 7. And I'm going to take the square root of that. And it's got an escape velocity of 60141 meters per second. So Jupiter has a much bigger escape velocity. I'm trying to get through this. I don't want to like be crunched on time. While the escape velocity is the velocity required by an object to escape the gravitational potential well of a planet, the binding energy is the amount of kinetic energy required to escape a gravitational potential well. The binding energy is how much energy you need to escape the well. So That's what binding energy is. Realize it's just the same thing as the gravity of the well, the potential energy of the well, just a positive value. That's how much energy you need to escape the well. For a satellite in orbit around a planet, its total mechanical energy is this. I was thinking for a long time why it's just half of the gravitational potential energy. And I think it's because if we're only talking about the satellite, we're only looking at half of its energy. It's taking one half of the amount of energy that's needed. If a satellite is in orbit around a planet, then the binding energy, or the energy required to escape the gravitational potential, is one half of the potential energy, or one half of the gravitational potential. That doesn't make sense what I said. Oh, yeah. The amount of energy required to escape is one half of the gravitational potential. That makes sense. So the difference between these two binding energies allows us to determine the amount of energy required to place a satellite into orbit from rest on a planet. So, that's not what I wanted to do. Okay, I'm back. Sorry, I just had to check on something. It's important to note here that this is talking about satellites that are in orbit. The fact that it's in orbit is very, very important to what is going on. These are for satellites in orbit. So when you have the binding energy, or the energy in total of an object in orbit, and you minus the total energy of the object on the planet, you're going to get the total energy required to move a planet into orbit, or the energy required to put something in orbit. The energy required to put something in orbit. So let's do a few questions. A 100-kilogram astronaut is initially at rest on Earth's surface before she is launched into space. What is her gravitational potential energy at this point? We've looked at like 100 formulas right now. Let's look at the one that's for gravitational potential energy. Oh, this one looks like it's for gravitational potential energy. It is negative GMM over R. Hold on, let me give myself a pause because someone's coming in. Okay, sorry, I don't know where I was. Me and Mr. Podunski were looking at my memes and talking about them and talking about how funny they were and our favorite ones. So I'm back on track. We were doing this question where we were talking about the gravitational potential of someone that is standing on Earth, or an astronaut that is initially at rest on Earth's surface and before she's launched into space. What's her gravitational potential at this point? Well, we know that the formula was negative G M1 M2 over R. So gravitational potential is equal to negative G M1 M2 over R. It is a 100-kilogram astronaut, which is a little bit on the heavier side, so it's a little bit lighter than Mr. Kegler. Is equal to negative 6.67 times 10 to the negative 11. That's the gravitational constant, 100 kilograms, and then multiplied by oh, the mass of the Earth. Sorry, I'm losing my mind here, you guys. Mass of the Earth. What's the mass of the Earth again? I should know these numbers. Mass of the Earth, 5.972 times 10 to the 24. Divided by the radius of the Earth, 6.371 times 10 to the 6. I throw that in my handy dandy calculator. 6.67 times 10 to the negative 11 times 100 times 5.97 times 10 to the 24 divided by 6.371 times 10 to the 6. Yeah, that works. I'm getting negative 6.25 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8, 9 times 10 to the 9 joules. We're talking about energy. Energy is always measured in joules. Sorry, coughing a lot here. The rocket that the astronauts is in achieves a geosynchronous orbit around Earth. I forgot what geosynchronous orbit meant. I was Googling it. What it actually means is it's just the orbit that follows Earth perfectly. It's an orbit around the Earth where the period is 1 day, where it'll go around at the exact same time that the Earth spins. That's geosynchronous orbit. It's actually very useful for satellites and making sure that your phones have the same carrier, and because it's going around at the same position as, like, so the satellites are in the air at the exact same time. It's very, 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 very useful in that regard. If she gets out of the rocket, what is her total energy while in orbit? So she's in geosynchronous orbit right now. We're talking about if for a satellite in orbit around a planet, its total mechanical energy is 1/2 g mm over r. Oh. So we know that the total energy, ET, phone, home, is 1/2 of g m1 m2 over r. Can you just take 1/2 of this value right up here? No, you can't, because it's now at a different radius, right? Excuse me. The radius is going to be 4.22 times 10 to the 7 over 6.67 times 10 to the negative 11, 111, no, just 11, times 100 times mass of the Earth is 5.972 times 10 to the 24, 1/2. Do 1/2 of that. I have 6.67 times 10 to the negative 11 times 100 times 5.972 times 10 to the 24 divided in half divided by 4.22 times 10 to the 7. I get a value of 4.72 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8. 8. That is her total energy while she's in orbit. Oh, if she gets, oh, because she's out of the rocket. Sorry, I thought I made a mistake. She got out of the rocket, so that's her energy while she's out of the rocket. Like the rocket is going like that, and she's here orbiting around. That's her total energy while she's out of the rocket. Does that kind of make sense? If she was in the rocket, I thought I thought I made a mistake because I thought she was still in the rocket. If she was still in the rocket, then what would happen is the energy would be a lot larger due to the fact that this number wouldn't be 100, it would be a much larger number. How much work must be done to launch the astronaut into geosynchronous orbit? 2 seconds. Oh, that's not what I wanted to do. Sorry, mistakes made. I also forgot that this is negative and negative. Okay, going from here. So that's how much energy she has while she's in orbit. How much work must be done in order to launch the astronaut into geosynchronous orbit? Well, we know that the work is the change in energy, and so that's going to be when she is in the energy of when she's in orbit minus the energy while she is on Earth or the surface of the Earth, right? You can kind of think of this as final minus initial. She's in orbit right now and she starts off at Earth. So we already said that the energy of her in orbit is going to be negative 4.72 times 10 to the 8. And we're going to subtract the energy while she's on Earth, which is 6.25 times 10 to the 9 joules. We get an answer of 2 seconds while I throw it in my handy dandy calculator. Five 0.78 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8, 9. That makes sense. And it's actually a positive value too. It makes sense that you need to have a positive amount of energy you need to do to get into orbit. Once she is in orbit, how much additional energy must she have in order to escape from the Earth's gravitational potential well? Well, this is how I like to think of it. This is how much energy she has while in orbit, right? So if that's how much energy she has while she's in orbit, she needs that much energy to escape the orbit. So she needs at least negative 4.72 times 10 to the 8 joules. Sorry, this video took a lot longer than I wanted it to. Give it a go. Try the questions on assignment 3. I'll be able to answer questions come tomorrow's MS Teams. Have a good day, you guys.